Okay, so we're going to talk about 16.9, 16.10, and this is going to help you. Well, see, there's not as much equation writing as there used to be, but this used to always help students with their equation writing on that particular section. So I actually did, for the next set of practice problems, I'm putting some equation writing questions like they used to have on the AP exam, just so you can get some practice with what exactly happens when you put an anion in water. But turns out, well, not anion, sorry, if you put a salt in water. But it turns out there are certain salts, you put them in the water, and they actually change the pH. It depends on the salt. Okay, there are certain salts that don't do anything. For example, I think with the last lab we just did, you guys, in one of the stations there was the bromothymol blue. The sodium chloride didn't really change the color at all if you tried the sodium chloride, because that's a salt that doesn't affect the pH of the solution. But there are certain ones that do. Okay, so anions typically are bases. All right, that's not always the case, but typically they're bases. And so what they can do is react with water in a hydrolysis to form OH- and the conjugate acid. Now, those of you who have been in Project Lead the Way classes are more familiar with hydrolysis probably, or maybe if you've taken, maybe anatomy and physiology or AP Bio, but I think most of the time people wait until their senior year to take those classes anyway, so you guys may not have had those yet. But all hydrolysis means is it's just separation of water. Okay, so what happens is, if you've got a base like X minus, whatever X minus is, it can take a hydrogen from the water. So now the water gets split, hydrolysis. Okay, and then you end up with HX and OH minus. So a lot of times when you put a salt into water, now sodium chloride's a bad example because, well, we'll talk about that in a minute. But if you put something like sodium fluoride into water, okay, as soon as you put it into water, the first thing it's going to do, because this is an ionic compound, it's going to dissociate. Na plus and F minus, right? Now the Na plus is just floating around in there. Doesn't really do anything. Again, we'll talk about that in a second. But this F minus right here can react with the water, and then you end up with HF and OH minus. Okay, so you put NaF, sodium fluoride, into water, it's going to make the solution more basic. All right, that makes sense? So this happens with anions. It can also happen with, you can have a trend for cations as well. Okay, so with cations, there's a couple of different things that can happen with cations. NH4 plus ammonium is going to act like an acid. Okay, it's going to lower the pH of the solution because you've got NH4 plus. It can give away one of those hydrogens fairly easily and form hydronium, H3O plus. Okay. Okay, yeah. Most metal cations that are hydrated in solution also lower the pH of the solution. Now, what hydrated means is essentially that they form a complex with water. Okay, so you remember the coordination complexes we've talked about? So any metal that will form a coordination complex typically will lower the pH of a solution. All right, now there's a, I think in the reading guide, I tell you to stop at that point, I think, and go over to the Lewis acids and bases stuff on page 705, because it talks about the hydration of these metal ions and how exactly that works. All right, so the example that they give is for something like, I think it's Fe2 plus. Is that their example? No, Fe3 plus. Okay, so you've got Fe3 plus. All right, you put that into water, and really you're not going to put Fe3 plus into water. So let's back up and take this from the very beginning, because there's kind of a complicated series of steps here. Probably what you would put in is something like iron chloride, right? So you put that into water, splits apart into Fe3 plus and Cl minus, and there'd be 3 of the Cl minuses there, so that's, yeah, I'll just put a 3 in front of there. in case that bothers anybody. The chloride ion is not really going to do anything because in order for the chloride to, now I guess I should have talked about this with the anions, but in order for the chloride to do anything in the water, it would have to take a hydrogen away from the water and form OH minus. Now why is chloride not going to do that? What happens if chloride takes a hydrogen away from water? What does it form? HCl. Well, that doesn't happen, does it? That's a strong acid. So if by taking a hydrogen it forms a strong acid, it's not going to take a hydrogen in water. Okay, so it doesn't change the pH. So there are certain anions, backing up to the anion thing for a second. Tell me some of the anions that wouldn't change the pH of a solution. You're going to have to think about your strong acids. Do we have these memorized yet? Yeah. Okay, so, well, okay, here's the thing with SO4. You picked the one that's diprotic, right? So SO4 2- will actually take one hydrogen and become HSO4-, right? It just won't take the second one and become H2SO4 again. But your other ones, I-, remember you can just kind of look below chlorine. You can look on the Br- and the I-, okay? So those two won't really change the pH of a solution. NO3- won't change the pH of a solution because that would form nitric. ClO4- would not change the pH of a solution, and most of the time, I don't know, maybe the AP curriculum writers disagree on this one, but according to your book, ClO3- wouldn't either, right? So those are your main, the chloride, and then those, 1, 2, 3, 4, 5. What am I missing? Oh, the H2SO4, okay? So I guess HSO4, well, see, I got to be careful with that one because that's amphiprotic, so, amphiprotic, sorry, amphoteric, and so that one could give away a hydrogen and change the pH, so maybe we just should forget that one altogether. But the other 6, we can say for sure that they're not going to change the pH of the solution because in order to do so, they would have to form strong acids, and they're not going to do that. Okay? So, all that to say...
Please report to the main gym. All custodians, please report to the main gym.
All that to say, the Cl- is out of the picture here. We don't have to worry about that because it's not going to change the pH. But we've got Fe3+ floating around in that solution. So what the Fe3+ does is it actually combines with water, and it's going to form a metal complex, Fe, H2O, I believe it's 6. Let me check and make sure. Yep. Which makes sense because that's twice the charge, right? So it forms this, okay? Now, what happens, if you think about this, you can end up with basically this iron is surrounded by 6 H2O molecules, okay? Because it's surrounded by those 6, it actually makes it easier for a water molecule to lose. How do I want to write this? How do they write it? Okay, you see they're not really showing the actual process here. So basically we've got something like this. Okay, and then you can think of it. Really, this is what's happening with all 5 of these as well. I'm just showing this one, okay? So what happens when this thing forms a complex, it actually makes it easier for the oxygen to lose one of its hydrogens, okay? So because of the electron density and the way that everything is here, this hydrogen can come off a little bit easier than it could when it was just connected to the water molecule, all right? So because that's the case, when you put Fe3 plus into a solution, it actually causes some H's to come off of some water molecules and form H3O plus with a different molecule. So then once this happens, then what you would end up with, and this is what's in the book, you'd have Fe H2O 5 OH, and now this is a 2 plus because we lost one of the hydrogens, and then you would have H3O plus hydronium, okay, because it would have connected to another water molecule. So because the Fe3 plus very indirectly increases the H3O plus concentration in the solution, it's going to be an acid, okay? And so any cation that will form a complex ion with water will do this exact same process, all right? So the metal cations that will not form a complex with water should be fairly easy to remember. They're the ones in group 1, okay? So everything in group 1, in other words, will not change the pH of the solution, okay? Because they don't form these complexes with water, okay? Group 2, below, or calcium and below on the periodic table, they also will not form metal complexes with water. All right? And I'm ashamed to admit, I don't know exactly why that is. Yeah, calcium and below. I'm going to have to look into that, because I should know why that is, but I don't. What's that? Well, maybe if I think about it enough, maybe I can figure it out, but for right now, I don't. So you're just going to have to take my word for it for right now, and I'll get back to you on that. But basically, what do you notice about these? Anything special about these that we've talked about earlier in this chapter? Especially the group 2 calcium and below, what does that sound like? Yeah, those are the ones that form strong bases when you put them with hydroxide, right? Okay? So there's some sort of correlation there. Group 1, group 2 calcium and below, the ones that will form strong bases when you put them with hydroxide are the ones that don't change the pH of a solution when they're just floating around as free ions. All right, so going back to the sodium chloride thing. Oh, I see, I decided not to do sodium chloride. But we talked about sodium chloride and the fact that sodium chloride doesn't change the pH of the solution at all when you put it in. The reason for that is it dissociates into sodium, which is in group 1, so that doesn't change the pH at all. And then it also dissociates into Cl-, which in order to change the pH would have to take a hydrogen away from a water molecule. That doesn't change the pH because it's not going to form HCl again, okay? So you've got 2 ions there that don't change the pH of the solution, so salt water is just as neutral as distilled water is. Does that kind of make sense? It's a little complicated, but the main things you really need to know here, cations tend to increase the pH. They tend to make it more basic. I said that backwards, sorry. Anions tend to make it more basic. Cations tend to make it more acidic. Okay, and that's the main thing that you need to remember. And then if you can remember the exceptions to that, then you should be fine. They like to ask that type of question on the AP exam, or at least they used to. Okay, so this is still talking about attraction between non-bonding electrons on oxygen and the metal. Causes a shift in the electron density. Okay, we talked about that already. So it shifts the electron density in the water, which makes it easier for one of those hydrogens to pull off. Okay? Makes the OH bond more polar, and therefore the water more acidic because the hydrogen will leave more easily. Okay? The greater the charge and the smaller the size make a cation more acidic. Oh, there it is. Yeah, there it is right there. So if you think about the group 1 metals, they all have a very low charge, right? Okay? So that's why they only have a +1. And then the +2s It can make a solution more acidic if they're smaller in size. Okay, but these are all bigger in size. The calcium and below are larger, so they're not going to make it as acidic. I guess even that is just giving you a rule. It's not really telling you why, though. So I'll stop looking at that. All right, is that making sense? All right, so then the effect of cations and anions. There's a good summary in the book, and I think this is basically just restating it. Anion that is a conjugate base of a strong acid will not affect the pH. All right, that's like Cl minus, I minus, Br minus, NO3 minus. An anion that is a conjugate base of a weak acid will increase the pH. All right, so basically anything besides those 6 or 7 that we talked about is going to increase the pH. In other words, cause it to be more basic. The cation that is a conjugate acid of a weak base will decrease the pH. Okay, so that's another way to look at it. If it's a conjugate acid of a weak base, it will decrease the pH. And cations of the strong areneous bases will not affect the pH. We already talked about that. Okay, that's group 1, and then calcium below in group 2. And then other metal ions will also cause a decrease in pH. When a solution, hang on just a second. Okay, sorry about that. Go back through this quickly. Okay, when a solution contains the conjugate base and the conjugate acid, so in other words, what if you have a situation where you've got a cation that decreases the pH, and you've got an anion that increases the pH? How do you know which one is going to have the greater effect? And so what they're saying here is the effect depends on the Ka and the Kb values. Okay, so you would have to know the Ka and the Kb for that in order to be able to figure it out. Okay. And I don't think that they're going to give you a problem like that on the AP exam. The ones that I've usually seen are the cut and dry, where they give you a salt where the cation is going to affect it, but the anion doesn't, or vice versa, and then you would just fairly easily be able to tell what's happening. So I've got some practice problems for you on that for tomorrow, I think. So hopefully that helps a little bit with, well, we're going to come back to that later. Now here's the part that I think is really going to tie some things together for you as far as why something is an acid, why something is a base. And actually, here's where we might get our answer for what I was struggling with before. We'll have to see. I'm going to have to think about this. But basically, the more polar the HX bond, so if we're talking about hydrogen attached to anything, the more polar that bond and the weaker the bond, the more acidic the compound. All right, so just kind of thinking about that, something like HCl. Okay, that's fairly polar because the chlorine is pulling the electrons a lot closer to itself than the hydrogen. Okay, now, a really stable compound has equal sharing of the electrons in between the two things, right? It's kind of like a stable relationship, really. If one person is hogging the electrons in the relationship, then the other person is more likely to leave, right? I know you've seen that a million times. Maybe not with electrons, but anyway, if people are, if there's not an equal give and take here, then that's not going to work out very well. And it's kind of the same way with these acids, right? So the chlorine is hogging the electrons a little bit. So the hydrogen, if it gets a better offer, it's going to take it, right? And you put it into water, and it's got a better offer, right? Because the oxygen's right there saying, I've got a lone pair of electrons right here, and maybe I'll share with you a little bit better than this chlorine will. Okay, so then the hydrogen will leave and go over to the water molecule, where it can have a set of electrons that it shares with the oxygen over here. Okay, and then chlorine's left by itself, and it keeps, floating around in the solution saying, no, come back, hydrogen, come back, and hydrogen won't, okay, because it's doing much better over here with the oxygen just completely wreaking havoc on any metal that it comes into contact with, or skin, or anything, right? Okay, hydronium's having a fun time just destroying things at that point. So anyway, that's I guess that's kind of a destructive relationship that hydrogen ends up being in, but you know, every analogy breaks down eventually. But that's kind of the idea, okay? Because these things are, you know, not equally being shared, that's not a great situation for bond strength, okay? And then the weaker the HX bond, also, another thing that can affect that, remember, is the size of the molecule. You remember talking about that earlier in the year when we were talking about the trends? The molecules that are have smaller nuclei, they're going to be stronger bonds, right? So you've got something like HF, that's a little bit stronger bond than HCl, right? Just because the fluorine is smaller, so the electrons are in closer, all right? So the sharing, it's a little bit better there because the fluorine's not quite so big, okay? So that's why hydrofluoric, you might think, because there's such a big electronegativity difference there between the H and F, you might think that that would be a strong acid, right? But the other factor that's going on there is that bond is actually a little bit stronger because the fluorine is smaller than the chlorine, okay? So you keep going down the chart there, you've got bromine and iodine, so that's why those are stronger acids as well, because the molecules just keep getting bigger and bigger and bigger, and the bigger they get, the weaker those bonds and the easier it is for the hydrogen to leave, okay? So that's, hopefully that helps as far as the trend. So you look, as you go across, increasing acid strength as you go across the periodic table. Now what's the reason for that? Yeah, more, say it again, more what? Okay, it's going to be more polar, right? You've got carbon and hydrogen right here. It doesn't really act like an acid or a base because carbon and hydrogen have a pretty stable relationship. Their electronegativities are similar. There's fairly equal sharing between the two of them, okay? So the hydrogen doesn't necessarily want to go anywhere. This helps you out a lot with organic molecules too, just trying to figure out what's going to happen with the organic molecules. Usually it's not the carbon and hydrogen bonds where the reaction takes place. It's usually somewhere else, like an offshoot from the carbon and hydrogen, like maybe an OH group attached to one of the carbons. That's usually where you're going to see all the action as far as the reactivity. Because this carbon-hydrogen bond is fairly stable. It's, you know, they're very similar in electronegativity. But the further over to the right you go, the more electronegative the anion gets, the more it's pulling those electrons to itself, and the more the hydrogen's going to tend to leave. All right? So going across, this polarity thing is probably the most important factor. Now going down, the strength or the weakness of the bond is probably going to be the most important factor, because the bigger these molecules get, the weaker the bond is going to be, and so the more acidic it's going to get. Okay, so you can see going down the table, things tend to get more acidic. Going to the right on the periodic table, things tend to get more acidic. All right. And again, that kind of explains why, you know, you go far to the left on the periodic table, and now you're dealing with the things that can attach to hydroxide and be bases. Okay. So that's that. Now, you've also got oxyacids. So we were talking about binary acids just then. Binary just means there's just two elements involved, okay? Hydrogen and something else. With oxyacids, it's a little more tricky because you've got to think about the molecule as a whole, not just kind of a linear relationship between two things. But what's going to happen is, let's say you've got something like HOCl, okay? Which is the way that would usually be written as an acid, HOCl. Well, the chlorine has a higher electronegativity than the iodine, so it's going to tend to pull the electrons towards itself, so that electron density shifts away from the hydrogen. Okay, so now you've got two things that aren't sharing very well with hydrogen, and the hydrogen says, forget this, I'm leaving as soon as I get the chance. And so and actually this is not that strong of an acid. It's actually fairly weak. It's 3.0 times 10 to the negative 8 for the Ka. But you compare that to iodine, the IOH down here. Because this doesn't pull the electrons as closely, then there's a little bit more electron density still left right here between the oxygen and the hydrogen. And so the hydrogen is less likely to leave. So it's got, a lower Ka. All right? So you're just kind of thinking about how electronegative is everything on that molecule that would be pulling things away from the hydrogen. And the more of them there are, and the more electronegative they are, the more likely it is that the hydrogen will leave. All right? So then you look at something like this, okay, and this is kind of an example of what I just said. So hypochlorous, we just talked about that, because you've got one chlorine basically pulling the electron density away from this bond right here, okay? But then you have chlorous, now you've got two oxygens, okay? So basically an oxygen and a chlorine that are now pulling the electron density away from that hydrogen-oxygen bond. And you just keep adding things to this, and it keeps getting pulled more and more away, and this bond gets more and more polarized, and then the hydrogen has a stronger tendency to leave, okay? So for a series of oxyacids, acidity increases with the number of oxygens as well. Sometimes resonance, well, and this is more stability, okay? So they talk about this in the book as well. If the conjugate base ends up being fairly stable, then that can make it more likely that a hydrogen would leave, okay? So this is more of like a hydrogen threatens, hey, I'm going to leave if you don't start treating me better, and, and then this anion here says, oh, we're just fine without you because now we can do resonance, and so that makes it more stable because now you've got these delocalized electrons that are kind of really in orbitals. They're sort of more in here, okay? Just makes it more stable, so then because that's the case, it's okay the way it is. It doesn't need that hydrogen there, so the hydrogen comes off more easily. So that's kind of the deal with carboxylic acids. That's why you need that double bonded oxygen there coming off of the OH group, because as soon as that H leaves, now you can start doing resonance between the two oxygens there, and it's more stable. All right, I think those are the main things that we needed to talk about there. Hopefully that makes sense. But I like this section because it really kind of ties some things together, the ideas of the periodic trends and some of that stuff. And we'll do a bunch of practice on this tomorrow in class because I've got a whole worksheet where it's just I give you lists of acids and you tell me which one is the stronger of the two. Without a Ka value, you should just be able to look knowing the trends and figure it out. Okay? All right. See you in class.